Welcome back to the Deep Dive. Today, we are opening up the hood of the Linux server and looking at the one component that I think keeps most system administrators up at night.
Which one is that? Security?
No, simpler. Storage. But not just, do I have space? We're talking about the file system itself.
Ah.
We're working off a really dense presentation deck today. It's titled Linux File System Integrity and Maintenance.
The 8.7 slides.
That's the one. And honestly, this isn't just about saving files. It's about keeping the whole engine from exploding.
That is a very fair description. People tend to treat the file system like this. It's this magic bucket. You throw data in, you pull data out.
Right.
But this deck makes it really clear that it's actually a living, breathing machine. It needs traffic control. It needs structural repairs and constant monitoring.
Exactly. So for this deep dive, we're going to do an audio walkthrough of this specific slide deck. We'll go slide by slide, hitting the commands and concepts you're absolutely going to see on the exam.
And in the real world, when your server dies at 3 in the morning?
Yeah, exactly. Sounds like a plan.
Let's do it. It's the best way to visualize the workflow.
So let's pull up the deck. We're looking at slide 1 and slide 2 to start. These kind of set the stage with the 3 pillars of file system management. The graphics are pretty distinct. A gauge, a wrench, and a speedometer.
Right, and these correspond to the 3 big questions every admin has to answer. So the gauge is capacity.
Do I have room?
Exactly. The wrench is integrity. Is the data actually readable or is it, corrupted?
And the speedometer is performance.
Why is my database suddenly crawling? Yeah.
Simple enough. Capacity, integrity, performance. Let's click forward to slide 3 and dig into that first pillar. Capacity. The slide title is Awareness, Quantifying Space.
This is where most people get a little overconfident. They think, oh, I know how to check space. I just look at the percentage.
But the slide uses this great analogy of a warehouse versus the inventory. It's drawing a distinction between the building and the boxes inside. Why is that distinction so necessary?
Because in Linux, you have 2 different commands to measure those things, and they don't always agree with each other.
Okay.
The command df, that's for disk-free, it measures the warehouse. It looks at the whole partition structure. But do, for disk usage, that one actually walks down the aisles and counts the boxes.
So df is the structural view, do is the content view. But hang on, look at the big warning box in the middle of slide 3. It says critical concept, inodes, and it calls them inventory tags.
Yes, this is the classic gotcha moment. An inode, or an index node, is basically the metadata for a file. Think of it like a shipping label or, sticky tag.
Okay.
When you format a hard drive, the system prints a specific number of these tags. That's it. You don't get more later.
So wait a minute, I could have a 10 terabyte hard drive.
But if you fill it up with millions and millions of tiny, 1 kilobyte text files, you might use up all of your sticky tags long before you fill up the actual shelf space.
And what happens then? What does the system do?
The warehouse just closes. You cannot create a new file. The system will scream, no space left on device, but you check DF and it says you have 5 terabytes free.
Wow, that is a nightmare to troubleshoot if you don't know what you're looking for. So how do we check the tags? The slide has a specific command highlighted here.
You need to memorize this one. DFAI.
Just adding that I.
That little I switches the entire view from blocks, which is shelf space, to inodes, the tags. It shows you the total, the used, and the free inodes.
And if you see that used percentage at 100%.
It doesn't matter how many gigabytes are free. You're completely dead in the water until you delete some files to get their tags back.
Okay, so DFI is the sanity check. Now, let's say we are actually out of space, like block space. We need to find the culprit. We're moving to slide 4, deep dive into directory sizes. The screenshot shows a terminal running do.
Right, do is the tool, but by itself it's incredibly noisy. It just lists every single subdirectory recursively. It'll scroll off your screen for days.
The slide highlights 2 specific flags here, A, N, and C. The command shown is doac home user. Let's unpack those.
So A stands for all. By default, do only shows you directory sizes, but often the problem isn't a directory at all.
It's a single file.
It's a massive rogue log file or a disk image just sitting there. If you don't use A, you won't see individual files and you might completely miss the real problem.
That's a good tip. And the C.
That stands for create a grand total. It just puts a handy summary line at the very bottom of the output. If you're scanning a whole home directory, you just want that bottom line number.
Right, you don't want to do the math yourself. So doac is the quick audit. Show me everything, including files, and give me the total.
Exactly.
All right, that covers the gauge. Let's pick up the wrench. We're clicking over to slide 5, starting the integrity section. The title is Examining the Blueprint, Dumpy Fiefs.
Okay, now we're getting into the real nuts and bolts of the X22, X23, and X4 file systems. dumpytooth is a utility that basically just dumps all the file system information, the superblock, the block groups, everything.
The slide shows a huge wall of text output, but then it zooms in on a very specific flag in the key command box. Dump it BC.
This is really important for troubleshooting hardware issues. The MythsB flag filters all that noise and asks just one question. Are there any blocks marked as bad?
Bad as in corrupted.
Bad as in physically damaged. If the hard drive controller realizes a sector on the disk can no longer reliably hold a charge, it marks it as bad.
So the file system knows to stay away from it.
Exactly. It stops trying to save data there. So if you run dumpytooth.de and you see a list of numbers,
You should probably go buy a new hard drive.
you should probably go buy a new hard drive. It means the physical media is starting to degrade.
Good to know. Now, slide 6 takes a slightly more optimistic tone. It's titled Changing the Engine, TuneToofs. There's a graphic of a mechanic bolting a new part onto an engine block.
This is one of the coolest features of the Linux file system, I think. Usually with other operating systems, if you want to upgrade your file system, say add a journaling feature, you have to back up all your data, wipe the drive, format it, and then restore.
Which is massive downtime, just huge.
Right. TuneTooth lets you change the parameters of the file system while the data is still there. You are tuning the engine without taking it out of the car.
And the example on the slide is converting from X2 to X3.
Right. X2 was the old standard. It was fast, but fragile. If the power cut out, you could easily lose data. X3 added a journal, which is basically a log that records changes before they happen. It makes the system much, much more robust.
And the command to do that conversion is highlighted right here. TuneTooth duty east
Just DGJ stands for journal. You run tune2fsdj on your device, like devs db1, and it just allocates space for the journal, creates it, and boom, you've instantly upgraded to an XD3 file system. No formatting.
That is incredibly slick. TuneTooth SDGJ.
Okay, moving to slide 7. We're stepping away from the X family for a moment. This slide is all about XFS.
XFS is the heavy lifter. It's the default file system for Red Hat Enterprise Linux. It's built for, huge data, massive files, high performance, but because it's a different architecture, your dumpytooth tools won't work on it. The slide is split into two sections: viewing parameters and a distractor warning. Let's look at the viewing part. I see XMessinfo. That seems straightforward enough.
Yeah, XFSinfo just displays the block size, inode geometry, stuff like that. But look at the second command there. XFSBetastat.
That's the one that seems weird. Grove sounds like I'm about to resize the partition.
And you normally would be. But that SM flag is the key. It stands for no change. It's basically a dry run. It simulates what would happen if you grew the file system, and as part of that simulation, it prints out all the current geometry.
So it's kind of a hack.
It's a very clever workaround. If you can't remember XDesInfo for some reason, you can always just pretend to grow the file system with skfn to see the stats.
And what about this distractor warning box at the bottom? It says in big red letters, do not use XFS metadump to view settings.
This trips people up on exams constantly. XS metadump sounds like dumpties, right? You think it's just going to dump the info to your screen.
It sounds exactly like that.
It is not. XS metadump is a serious debugging tool. It's used to copy the entire metadata structure to a file so you can send it to a developer for analysis.
So it's for forensics, not for a quick check.
Yeah. Forensics not for checking your block size. Use XSinfo to look, XS metadump to copy for support.
Got it. Okay, we've looked at the blueprints. Now things are going wrong. We are moving to slide 8, and we're entering the emergency room. The slide title is Corruption Recovery.
This is where the sweat starts to bead on your forehead.
There is a massive golden rule printed here. Never run repair tools on a mounted file system.
This is rule number 1, 2, and 3. The standard repair tool is sex file system check. If you run this while the drive is mounted and the OS is actively writing to it, you are going to destroy your data, period.
The analogy I've always heard is trying to change a tire while the car is moving down the highway.
It's so much worse. It's like performing open heart surgery on a runner who is in the middle of a marathon. The file system is changing under your feet while you're trying to stitch it up. You'll end up with cross-linked files, corrupted everything. It's a disaster.
So the slide has a little flow chart. Step 1, unmount. But what if the corruption is on the root partition, the one you're booted into? You can't just unmount the floor you're standing on.
Correct. And that's why the flowchart points to the other option, single user mode.
Explain what that is.
Single user mode is a special boot state. It shuts down the network, it logs off all other users, it kills background services, and most importantly, it mounts the root file system as read-only. That is the safe state you need to be in.
So if it's a data drive, unmount it. If it's the root drive, you have to reboot into single user mode.
Exactly. Then and only then do you run Flisk.
Okay. Now, slide 9 covers a specific worst-case scenario, superblock failure. We said the superblock is the blueprint. If that blueprint is gone, is the drive just bricked?
It certainly looks bricked. The OS will look at the drive and just say, I don't recognize this. It seems unformatted.
But the slide shows a solution. Backup superblocks.
The engineers were smart. They knew the superblock was a single point of failure. So when the file system is created, it sprinkles copies of the superblock all over the drive at specific block intervals.
So we have spare keys hidden under all the doormats.
A whole lot of doormats, yeah. The command to use them is E2SEAC.
HB again. We saw that with dumpifs.
Context is everything. With dumpatives, deputy meant show me bad blocks. But with E2SC, the repair tool B stands for backup superblock. You follow it with a block number, like E2SCEC32768 devs to 1.
And you're telling the tool, ignore the main map, it's garbage. Use this copy at block 32768 instead.
And, 99% of the time, that brings the drive right back to life.
Amazing. But what if it doesn't? Slide 10 is the nuclear option, surgical intervention, debugs, and it specifically calls out catastrophic mode.
Debugs is an interactive shell. It lets you manually edit the file system structures. It's dangerous. But the catastrophic mode on the slide is for when the drive is so mangled that normal tools will crash just trying to look at it.
The command is debugs DayC. What's the EC do?
The DayC flag tells the tool, look, don't read the bitmaps. Don't try to verify the inode counts. I know they're broken. Just open the drive so I can try to salvage one file.
So DayC8 opens the file system without checking if it's even valid first.
It's the break glass in case of emergency tool.
Wow.
You use this when you are trying to copy your resume off a dying drive just before you throw it in the trash.
Wow. Okay, let's assume we fixed the drive. We're moving to the final pillar, performance. Slide 11 is titled Traffic Control, I/O Scheduling.
This is a shift from software back to physics. A traditional hard drive has a spinning platter and a mechanical arm that has to move back and forth to read data. That movement takes time. It's called seek time.
And if you have a busy server, that arm could be just thrashing back and forth like crazy.
Exactly. The scheduler is the piece of software that acts like a traffic cop. It organizes the line, it looks at all the read and write requests coming in and says, hey, these 3 requests are physically close to each other on the disk. Let's do them all at once, even if they didn't arrive in that order.
It's optimizing the path of the arm. Now, the slide shows how to check who's currently in charge. You run cat sysblocks dbq scheduler.
And you'll see a list of words like noop, deadline, CFQ, but notice the brackets.
Yeah, in the screenshot, CFQ is inside square brackets.
That is the universal Linux sign for active. Whichever one of those words is in the brackets, that's the scheduler currently running the show.
Okay, let's meet the candidates. Slide 12 profiles the deadline scheduler. It has a graphic of a conveyor belt with little clocks on the packages.
The deadline scheduler is trying to solve a very specific problem called starvation.
Starvation.
Imagine a request comes in to read a tiny file, but the disk is just slammed, writing huge backup files. That little read request could just sit there forever. It starves.
So how does Deadline fix that?
It stamps every single request with an expiration time, a deadline. For reads, it's usually 500 milliseconds. If a request sits in the queue too long and gets close to its deadline, the scheduler panics.
It panics.
It basically stops everything else and shoves that request to the absolute front of the line immediately.
So it guarantees latency. The slide says this is best for read-heavy workloads, like a database.
Right, because you never want your database query to hang forever just because the system is doing a backup somewhere else.
Now, slide 13 lists the roster of the other 2 common schedulers, CFQ and Noop. Let's start with CFQ.
CFQ stands for Complete Fairness Queuing. This one is the diplomat. It creates a separate queue for every single process running on the computer. Then it just services them in a round-robin fashion.
One for you, one for you, one for you.
Exactly. It makes sure that no single application can hog the entire hard drive. It's the default for most general-purpose systems because it keeps everything feeling smooth.
And finally, Noop. The slide says it stands for No Operation.
It's basically a FIFO queue. First in, first out. It does almost no sorting at all.
Why on earth would you want a dumb scheduler?
Two very specific reasons, and they were both listed on the slide. First one, virtual machines. If you're a guest VM, the host computer underneath you already has a smart scheduler.
Ah, so you don't want a double schedule.
You don't want to waste CPU time sorting the requests just for the host to resort them all over again. So for VMs, you use Noop.
Makes sense. And the second reason?
SSDs. Solid-state drives.
Oh, of course, because there is no moving arm.
Exactly. There is no seek time. Reading data from one end of the drive is just as fast as reading from the other. All that complex math to minimize arm movement is totally pointless on an SSD. It just burns CPU cycles for no reason.
So on modern flash storage, dumb is actually faster.
It is.
We've reached slide 14, the cheat sheet. This is the rapid-fire summary. I'm going to run down the list. You give me the one-line takeaway for our listeners. This is the stuff for the quiz. Ready?
Let's do it.
Capacity. .dfii.
Checks for inode exhaustion, the out-of-tags problem.
Capacity.dse.
Shows all files, not just directories, and gives you a grand total at the end.
Integrity. Dump into's Miss BB.
Lists only the blocks that are marked as physically bad.
Repair DF tune Tuesday.
Adds a journal, converting an X2 to X3 file system on the fly.
Repair. E2 SEC she B.
Uses a backup superblock to restore a corrupted partition map.
Repair. Debugs Miss E.
Catastrophic mode. It opens the file system even if the bitmaps are completely destroyed.
And finally, scheduling. The brackets hat.
The text inside the brackets is the active scheduler.
That brings us to slide 15, the conclusion. Maintain space, ensure integrity, optimize flow.
It's a great summary. You know, we started this by saying the file system is an engine. And like any engine, if you just ignore it, it will eventually seize up on you.
But if you monitor your inodes, check for bad blocks, and pick the right scheduler for your workload,
It'll run forever.
I want to leave everyone with a thought that came up during that scheduler discussion. We talked about how the Noop scheduler, the simplest one, is becoming the standard for modern NVMe and SSD drives.
It's a fascinating trend, really.
For 30 years, we developed these incredibly complex algorithms, CFQ and Deadline, to manage the physical limitations of spinning metal. But now the hardware has evolved so much that the smart software is actually the bottleneck.
It really is. We are entering an era where the best way to manage storage performance is to just get the software out of the way and let the hardware scream.
It makes you wonder what other smart optimizations we're still holding on to that are actually just slowing us down now.
Something to think about. Thanks for walking us through the slides today.
Always a pleasure.
Make sure to check the show notes for a link to that 8.7 slides PDF so you can review the visuals yourself. Thanks for listening to The Deep Dive, and we'll catch you on the next one.